Hi students, welcome to Optimization Tutorial 24. Today we are going to discuss the very important topic of numerical differentiation. And this is a topic not only important in optimization but also in many fields in computational science. I am Dr. Ganguly. Now in today's tutorial we are going to discuss the different finite difference methods for numerical differentiation. And we are also going to compare the results of these methods to the exact solution which we can obtain by differentiating the function. Then we are going to look at the BFGS method and we are going to see how the finite difference derivatives perform when they are used in a typical numerical optimization method. So we are going to take recourse to Python code to illustrate these concepts. Now just to recapitulate on the BFGS method, you have the search equation given by xk plus 1 equals xk plus alpha k dk, where of course xk is the current point, xk plus 1 is the next point, alpha k is the one-dimensional search step, and dk is the search direction. And in the BFGS method, we obtain dk by solving this linear system. bk dk is minus ck. So of course bk is a matrix which is built up during the process of optimization here, and ck is the gradient vector. So one of the most important things in optimization is coming up with this gradient vector. Of course, when you have the function in an explicit form, this is a simple task. You can use your high school knowledge of differentiation to do that. But in many cases, it's not possible to differentiate the function. And in those cases, you have to use numerical derivatives. So today's problem is very practical. So stay tuned till the end of the video to learn about this subject. Now, of course, you can look at optimization lecture 24 on numerical differentiation for the background on this topic, and also look at lecture 23 on the BFGS method to again get a good background on BFGS, though we are going to discuss some of the aspects as we go in today's video. So let's take a look at the three finite difference derivatives. So essentially you have the forward finite difference formula, you have the central finite difference formula, and you have the backward finite difference formula. The derivations are given in lecture 24. Now if we look at these formulas, they are essentially based on the basic definition of the derivative. If you remember from calculus, as h tends to 0, this actually is going to become exactly equal to f dash x. But what we do in numerical differentiation is that we take h to be a small number, and then essentially these formulas are going to work. Now of course you can see the forward difference and the backward difference are simple representations. You can obtain all these from Taylor series, and the central difference formula is somewhat more complex, but it is also a more accurate formula. Now, presuming that you know the function value of a given problem at f of x, in forward difference and backward difference, you need to perturb this x in the positive and the negative direction. So you need to calculate one extra point. But in the central difference, you actually need to calculate two extra points here. So there is x plus h and there is x minus h. So central difference, of course, is more computationally expensive as far as numerical differentiation is concerned. Now in optimization, we generally use partial derivatives because we deal with multivariate functions which have more than one design variable. So in that case, you can obtain the partial derivative using this formula here. So what you do is that when you want to obtain the derivative of the function f with respect to the design variable x of I, you perturb this x of I by h here, and then as far as this f x0 is concerned, it simply remains at the value x0 here. Now this is the equation you will of course use when you are doing the forward finite difference calculation, and one of the recommended things is to use a value of h such as 10 to the power minus 4. If we presume the precision in the computer is 10 to the power minus 8, rule of thumb is that h can be square root of this epsilon p here. So this is a decent value to use in many cases. Of course it will vary depending on the function concerned, so that's something to keep in mind. Now if we want to use the central difference formula to calculate partial derivatives, we have to perturb x of I by h here, that is in the positive direction, plus h, and also perturb it in the negative direction, that is minus h. We need to subtract these two function values and then divide by 2h here. So one of the things about numerical derivatives is that you of course use only the function values here. You are presuming that you do not know the exact gradient. But for the problems today, we are actually going to calculate the exact gradient and then we are going to compare the numerical derivatives, so we know how these things work out in practice. Let's briefly review the BFGS method because we are going to use it today to showcase the numerical derivatives. So in this method, you start out with B0 is I, that is the unit matrix, and then you build up BK using this formula here, that is BK plus 1 is BK plus this matrix and this matrix. Now these two matrices are built up by using the information Sk and Yk. These are two vectors. And you can say yk is the difference between the gradient vector at the k plus 1th point at the kth point, and sk is actually the same as xk plus 1 minus xk. So that is the difference in the design vectors at the kth point and the k plus 1th point. So using this information, this particular matrix is built up, and as far as the BFGS is concerned, for many problems, especially problems which are quadratic, it's going to essentially build up the Hessian matrix by the end of the convergence process. So we are going to use that to check out the methods today. So let's start with the first question, and this question is to write a Python program for the forward, central and backward finite difference formulas, and we want to find the derivatives at a given point. So we choose the point 5 and minus 5, and we are going to use the following function given here, and I'm also going to use a value of h of 10 to the power minus 4. Now this particular function I have created such that the h matrix comes out in the terms of e, pi and so on. So that's something we are going to check later. Anyway, this is a quadratic. Let's look at this function carefully. So if we take this function and we take the gradient vector and set it to 0, we immediately see that the stationary point is given by 0, 0 here. So if we solve these two equations, we are going to get x1 equal to x2 equal to 0. Now, of course, we can see this is the stationary point, and to see if this is a minimum point or not, we need to calculate the eigenvalues of the Hessian matrix to check out if this is positive definite. So I have simply done this here in Wolfram, and these two have come out to be positive, lambda 1 and lambda 2. So this tells me that as far as the H matrix is concerned, it is positive definite. So we are dealing with a minimum point here. Now let's proceed with building up the Python function. So the first Python function essentially gives me back the mathematical function. So I have coded it in here. Now Python has some built-in numbers, for example numpy.e, numpy.py, which I use here, and of course x1 and x2 correspond to x0 and x1 in Python. So with that I can simply return the function using this formula here. Now the next thing I need to do is return the gradient vector. Now as far as this function is concerned, I can differentiate it. It's a very simple function, so I can use my knowledge of calculus to differentiate this function. And here what I do is that I have this Python function which returns to me the gradient vector. So again you can see this is ex1 plus pi x2, and this is going to be 7x2 plus pi x1. Now we are going to write some functions for each of the different types of derivatives. So let's start with the forward finite difference function, which I am calling FFD. This function takes values of x and h, and it's going to return to me the finite difference derivative. So in this case, you can see here, this is the function here. And so I'm taking this value of x and I am then returning the gradient vector here. Now, though I have written this in one dimension, you can see that you can extrapolate this concept in your mind to any multi-dimensional problem which I have done here. So what I have done is I have perturbed x by 1 and 1 here. In the first case, it is perturbing the x1 variable. In the second case, it is perturbing the x2 variable. And then I simply calculate this here by taking fx1 minus f of x divided by h and fx2 minus f of x divided by h. So in the first case, I am perturbing the x1 variable, and in the second case, I am perturbing the x2 variable. And both these are of course being perturbed by the amount h, which is a small number which is coming into the function here. And the function is going to return the gradient vector in this problem. Let's write a similar function for the backward finite difference formula. So this is the formula here for one dimension, and so I can very easily write a code here very similar to the previous code, except now there is a negative perturbation in these variables. So x1 is perturbing the first design variable, x2 is perturbing the second design variable, and then I am using this equation here, fx minus fx1 by h and fx minus fx2 by h to get the gradient vector, which is being returned by this BFD function. Now let's take a look at the central difference formula, and this formula is given here for the one-dimensional function, and I can write the corresponding Python function here. Now in this case there is a little bit more complexity, so essentially what I have to do is I have to perturb each variable, for example on the positive side. So the first two terms here, x1p and x2p, are perturbing in the positive direction the x1 and x2 variables, and the second two terms x1n and x2n are perturbing the x1 and x2 in the negative direction. So once I have these, I can very easily write the gradient vector here. So I have x1p, the f value minus f value x1 m, and this is divided by 2h, and similarly I have the value here for the second variable. So this should hopefully return to me the gradient vector for the function in this case. We are going to check all these things out with the actual derivative. So I have written the main program here. I import numpy first. I have the point as 5 minus 5. I set h is 0.0001, and then I essentially invoke these functions. So ffd, bfd and cfd, and I store the values in forward, backward and central. Now also I have the gradient vector, which is known exactly for this simple function here. So I call it using grad f and x0. Now one of the things I need to find out is how close these vectors are to the actual gradient vector. So for that I define this norm, and this norm is simply the difference between the norm of the finite difference versus the exact solution. So this is what I have put here, and then I print out these numerical gradients for the given problem. So I print out the forward difference value, the backward difference value and the central difference value, and then I also print out the exact value for the gradient C. Let's take a look at this. So you can see here the numerical gradients are given here. You can see that these gradients, which are calculated by forward finite difference, backward finite difference and central finite difference, they are all very close to the actual exact solution, but the central finite difference is virtually same or is exactly same. So you can see as far as the correctness of the solution is concerned, the central finite difference is extremely good, and the forward and backward difference are also reasonably good. Now one of the reasons for this is that as far as the forward finite difference, the backward finite difference are concerned, the error term there is proportional to h, whereas in the central finite difference it is proportional to h square, and also there is the issue of the derivative. So here it is proportional to h into second derivative, here it's proportional to h square into the third derivative. So again, if a function is relatively simple, if it's a quadratic function, then essentially the central finite difference is going to work out very well. So you can see it from this expression here. Now let's take a look at the next question, which tells us to modify the numerical derivatives computer program and check out different values of h, for example from 0.1 to 1e minus 8. And we are going to do this using this function here, x1 squared plus 2x2 squared plus e to the power minus x1 minus x2. And we are going to use this x0 value to calculate the derivative at this point. And of course, the epsilon value has to be calculated. That is the norm of the difference between CFD and C. CFD is the gradient obtained through finite difference, and C is the exact gradient which we obtain by differentiation. Let's code in the function and the gradient. So we have coded these in Python. So this is the Python function for the function, and this is the Python function for the gradient. So of course we have used NumPy here because NumPy is required to calculate the exponential function in both these cases. Let's write a main program for this problem. So what I do here is I have x0, that is the starting value, and I also create a list. So this list, which I call h list, has numbers from 0.1, 0.01, 0.001 all the way to I think 701. So this is actually a list at which I will run the code and see how it behaves. So then I have a for loop for h in h list, and then in each case for each h I invoke the different functions. So the forward difference, the backward difference, and the central difference. And I also calculate the gradient vector, and then I essentially print out the values of epsilon here. So for forward difference, for backward difference, and for central difference. So let's take a look at all these values, and though these numbers are small, we are going to look at these numbers once again more closely. But the main point here is that you can clearly see that the central finite difference tends to be much better in most cases. Again, remember, because of this particular dependence on h square. But one of the interesting things I want to show you here is that, of course, it's good to reduce h. But if you reduce it beyond a certain point, then the epsilon value again starts going up. So this is because there is always the balance between truncation error and round off. So round off is happening because as far as the computer is concerned, it's finding two numbers to be very similar to. So what starts happening is that fx plus h and f of x, they become more and more similar. So you will see this value will typically decrease, but then after a certain point it will actually start increasing. So that is some optimal value here, which would probably be good. But in most cases you can choose a reasonably small value for h. For example, if we select 0.0001, you are going to get pretty good estimates for the derivative for most functions out there. Now let's turn to one more question, question number 3. And that question tells us to take these three finite difference method and find the optimal value of h for the same problem, that is fx is x1 square plus 2x2 square plus e to the power minus x1 minus x2 and same point 5 minus 5. So let's check out this problem. So I have slightly modified the main program here. So in this main program, what I do is I have x0, I have c, and I have h list here. And then I have a loop for each of the problems. So I essentially print out forward finite difference, and then for h in this h list here, I print out the value of h and I print out the epsilon value for the particular problem. I then repeat it for backward finite difference formula and for central finite difference formula. And so I'm going to now print these in three different slides, and let's take a look at as to what value of h is best for each case. So let's look at the forward finite difference first. So here you can see the h value has been decreasing all the way from 0.1 to 1e minus 8. And the epsilon value is given here. So of course at h is 0.1, it's a very rough approximation, and soon as you start reducing h to 0.01, 0.001, you start getting better values. So at h is 0.0001, you have a pretty reasonable value. Now as you expect, the epsilon keeps going down, but you will see that after a certain point, for example, between h is 1e minus 7 and 1e minus 8, the epsilon value actually goes up. So here we have located the optimal point or the minimum point here. For this particular case, h is 10 to the power minus 7 is actually a very effective value if you are going to use forward finite difference formula. Now remember, all this is very function specific, so whatever I am telling you here is function specific, but it's showing you that there will generally be an optimal value for a particular problem. It will be specific to the function and to the point also, so both these things will be important here. Let's take a look at backward finite difference. Again, you find the same thing, that the h decreases here, so epsilon decreases. But if it crosses a certain point, you can see it increases between these 2 points here. That is 10 to the power minus 7 and 10 to the power minus 8. And so we can see here again that 10 to the power minus 7 is a pretty good point here. Now for central finite difference, one of the interesting things is that epsilon is pretty good or pretty small even at 0.1 and 0.01. So this is one of the reasons why central finite difference is often preferred. But one thing I should say, it is often preferred more in fields like computational fluid dynamics or computational science, where quality of the derivatives is very important. In optimization, sometimes the quality of derivatives may not be so important. So again, this is problem specific. And so sometimes you can use finite difference and get good results. I mean forward finite difference or backward finite difference, because the optimization algorithms are simply using the derivatives as a search direction. So sometimes it works out quite well. So again, if we see the numbers here, we can see that somewhere near this point here, it's of course going down, and then here it goes up. So between 1e minus 5 and 1e minus 6, actually the epsilon value has gone up. So we can choose then 1e minus 5 as the optimal value for the central finite difference method. So again, different values of h are appropriate for different methods out there. But like I mentioned, if you do not want to do all these kind of studies, you can often use a value such as 0.0001 or even 0.001 to get reasonably good results. Now that we know a lot about the different numerical derivatives, let's use it in a actual optimization problem. So question 4 tells you to use the BFGS code for the following function and starting guess, and compare the exact and finite difference gradients and check the B matrix at convergence. So this would be something interesting to see. Here, if you think about it, as far as the BFGS code is concerned, it knows nothing about the gradient vector as far as exact solutions are concerned. So it's going to build up the B matrix completely from numerical information. And of course, the function I have chosen is this. X0 is 5 minus 5, and I'm going to use the h value of 10 to the power minus 4. Again, the h function, or rather the h matrix, is given as follows. The h function in Python is coded in here. So this is a very simple matrix, e pi pi 7. So I have numpy e, numpy pi and 7 here. Now one of the reasons I selected this particular function is that if the method is going to build up the H matrix, then my B matrix should actually come out as this matrix, and I will be able to immediately recognize it because we know the numbers pi and e. I'm going to use one more function here, that is f1d, and this function is going to return the function value at the point xk plus alpha k dk. So this is going to be called in the one-dimensional search. Now for the one-dimensional search, I use this simple search function here, and what this function does is that it starts for a value of alpha, delta, 2 delta, 3 delta, all the way like this, and so it brackets the minimum between the points q minus 1 delta and q plus 1 delta, which you see here. And then what it's going to do, it's going to progressively reduce the delta by dividing delta by 10, and then continue the process until it has converged to some value a star or alpha star. Alpha star is given by this formula here, and it's going to continue this process till, as far as the bracketing is concerned, the value of I, it's going to be lesser than the tolerance value which I'm feeding into the main program. Again, check out optimization tutorial 7 for more details on the 1D search. So now one of the things I'm going to do to write clean code is that I'm going to define a function called grad numerical, and it's going to take in x, h, and the method. And if the method is forward finite difference FFD, it's going to basically call the FFD function and return the gradient vector. If it is the backward finite difference, it's going to call the BFD function, and if it's the central finite difference, it's going to call the CFD function. Now, just to recapitulate the BFGS formula, I will need to start with B0 is I. I will need to build up these two vectors Sk and Yk, and then I will need to update the B matrix using this formula here. So this is the BFGS function, which I have slightly modified from some of the functions you have seen in the past. So here, of course, I have to start with B0 is I, which is done here. I use the np.eye function to create an I matrix of size 2, and then I build up the Sk and Yk directions here, and then I invoke this BFGS formula here, and then we are able to solve the system BD is minus C in this location, and then I call the one-dimensional search, and then I can check out convergence in case the function value of the point x and the older point x old, which I have saved here, becomes less than the tolerance. Now the interesting thing here is that I am using C from numerical gradient. So I have put in this function here, that is grad num. This is taking x, h, and method, and now h, method are coming in through the argument list of BFGS, and of course x is starting at x0 and then continuously building up in this particular for loop out here. I'm also going to print out the exact value of the gradient that is going to come from the grad f function, and I'm going to print out the exact value of the gradient as well as the numerical value, and at the end of the process, when I have converged, I am going to print out the B matrix, which has been calculated by BFGS, and I'm going to print out the H matrix, which we actually know exactly for this problem, and it will be very interesting to compare these two. And I'm going to run this case for the three different finite difference methods. So let's do that. Let's start with the backward finite difference. So here you see I have put method is BFD. I have taken starting point at 5 minus 5, and I have put h as 0.0001, and I'm going to print out BFGS method numerical gradients method equal to, and then print this method here. So this method is basically a string here, and then I'm going to invoke the BFGS function. It's going to take in x0 the starting point, the tolerance value and the tolerance 1D value for the one-dimensional search and for the fact that the function has converged. And I'm also going to use this max, which I'm using in the for loop, and the value of h and method are also going in. Let's check out the BFD result. So you can clearly see here that the BFD is being used, the backward finite difference, and I am essentially starting from this point 5 minus 5. If you look at the gradient comparison between the exact and the numerical, you see they are quite close, and sometimes they become somewhat different. When you are very near convergence, you are near the root. Remember that the gradient is going to be close to 0. So this is a kind of very shallow region out there. So the fact that you are perturbing h by a very small amount, your numerical derivative may not be as good as the exact solution here, at least for the forward difference and the backward difference cases. But the most interesting thing which I like about this problem is that the B matrix and the H matrix have converged, and at this point you can see B equals to H, and the BFGS method has actually built up the Hessian matrix, and you can see these nice numbers here, which are pi 3.14159 and E, which is 2.7182. So these numbers have been built up by the BFGS all on its own by using the numerical gradient. Now if I want to use the FFD method, all I need to do is change method is FFD here. Remaining things remain the same in this main program. I run this code, so I have the method is forward finite difference, and you can see the numerical derivative is pretty close to the exact solution, and you can also see that I am getting the B matrix to be exactly equal to the H matrix here also. So this is again very interesting aspect of this problem. Of course, the converged solution is pretty close to zero. I should say it is zero for most practical purposes. But you are going to see in central finite difference, this is going to be really zero. Let's take a look at that, the central finite difference formula. So we put method is CFD, and then I put method here and then invoke the BFGS algorithm here. So now when I use the central finite difference formula, the derivatives are extremely good. So you can see here the derivative values, including the value when I is 2, that is you are very near the minimum point. They are extremely good. So this is the advantage of the central finite difference formula. And of course, you also see convergence is extremely good. You have now converged to e to the power minus 15 and so on. So this is actually zero, or at least zero as far as mathematicians are concerned. And if you look at B and H matrix, they are also exactly same. So in fact, we even got 7 and 7 here, no 6.999 and so on. So literally we can get the value of pi and E from this particular calculation. Now for the homework problem, I'll give you this interesting problem. You will see that as far as this function is concerned, if you use the central finite difference formula, this function is going to work extremely well with the central finite difference formula for various different values of h, including values such as 0.1 and so on. And I want you to figure out as to why that is so. So again, the answer lies in some of the theory behind this particular method, and take a look at the epsilon t term for this central finite difference method in numerical differentiation. We talked about that today also. So to summarize, we saw today that the important numerical derivative methods include forward finite difference, backward finite difference, central finite difference, and we wrote Python code for these methods. We used it in the BFGS method, and we saw that any optimization method can basically work with numerical derivatives out there once you have created some functions to calculate the numerical derivatives. Of course, using numerical derivatives is going to increase your computer time to some extent because you need that extra function calculation for perturbing f of x to f of x plus h. And in the case of central difference, you also have to perturb to fx minus h. So these are additional computations you have to perform. But in many cases, what happens is that your function value may be calculated using some computer program, and therefore you never really know the exact function out there or the mathematical representation of the function, and in those cases numerical derivatives have to be used, and that I would say is the situation in probably 99% of the practical problems as far as the real world industry and so on is concerned. And of course, remember, with all these methods we have done, the gradient vector is extremely important. The search direction here, for example, depends on the gradient vector. So like I have mentioned to you before, as far as optimization is concerned, gradient is king. And so take a look at optimization lecture 24 to check out numerical differentiation method. Now before I leave, I should mention to you that there are certain methods called complex step derivatives which are even better than the methods we talked about today. They use complex numbers, and in fact I have written some code in Fortran and I have made a tutorial on that, and I'm going to leave the Fortran tutorials at the end of this video and in the description box. And so you can check that out. If you look at the Fortran tutorial, you can of course write your own code in Python also there. And hopefully if I get time, I will make a Python tutorial on the complex step derivative. And I will see you in my next video sometime soon. See you then.